great workshop. For me, it's been really very enlightening, and I really learned a lot these last couple of days because my background is in survey statistics, and so I wouldn't really consider myself as being an expert in differential privacy. I maybe read the 6 papers that John mentioned appeared in the statistical journals, but definitely not even far less than 1% of the 40,000 that appeared in the computer science journals. And so I have a little bit of a background on differential privacy, but yeah, I know a handful of DP algorithms. But I'm definitely not the one to propose new algorithms. My perspective is more from the end user of the data. So what would be things that I would consider useful properties of the noisy data that you get, so that users can get the best out of it. And that's basically what I'm going to talk about today. And I'm starting this off with this title of a talk that John gave last year, because I don't really know at the exact date when this was announced, but I thought this has been really a game changer in many ways. From our perspective, so I worked on the statistical disclosure control side for many years, because we've been thinking quite differently about what it means to protect the data, thinking about what are sensitive variables, etc. So it was really a different perspective. So for us, it's a big change, but I also think it's a big change for the differential privacy community, because I think you have to think differently about what the final usage of the data will be. If you think about applying differential privacy at statistical agencies. And the users are just so different, and they have different expectations, they have different analysis goals in mind. And so I think this is really something that needs more attention in my view. And so what I think is that so far the focus often has been about drawing conclusions regarding only the units in the database. So it was not so much about trying to think about what it means in terms of getting inference regarding an underlying population. We had some talks yesterday that provided a nice exemption from that, and I really liked that, because I really think this is something we should think more about, as I said, from a statistical perspective, from a statistical agency's perspective more specifically. And then often I feel when I read these papers, it's really from a machine learning perspective. So thinking about users want to run some kind of machine learning algorithm in the end, and then trying to evaluate how close will the results be on the noisy data compared to the original data. And with machine learning, I think the major goal is often prediction. And I would say from a statistical agency's perspective, that's not always the main goal. And so often we have, as a utility measure, some information about, what's the maximum difference between the estimate I get from my noisy data compared to the estimate to the true value, basically, right? And I think this is not always the ideal measure if we are looking at that from a statistical perspective. Because at least in applied statistics, I think the major goal is often trying to make inference regarding an underlying population. So you have a clear population in mind, and you only have some sample data, survey data specifically, for which you would try to then get back to the true value in the population, making inference to that true value in the population. And so there's a lot of hypothesis testing. You want to test whether you have a significant effect, whether the conclusions you draw based on your sample actually are also important regarding the underlying population, or whether you might only have some random effect seeing that only occurred because of the sampling. So you have sampling uncertainty in your estimate. And then we're really interested in trying to identify causal relationships. And I think that's the major difference compared to trying to get good predictions, is that you really try to measure what's the effect of this and this variable on this and this outcome variable. And so what we are really concerned about is trying to quantify the uncertainty that we have in the conclusions that we draw. So some people would say statistics is about quantifying the uncertainty. That's all that statisticians do. And I agree to some extent. So it's really, we want to know if we have a result, we get an estimate, we want to know what's the uncertainty in that estimate. And so in that sense, valid variance estimation is of central importance in statistics. So we want to make sure we can quantify the uncertainty in our estimates. Okay? And this is something that, I mean, of course, the way I describe it here, it's a little bit like black and white, that it's not true that nobody thought about that before. There are obviously papers on that already. But I think there's much more research necessary in that area. And if you think about official statistics specifically, so statistical agencies, there are a couple more distinctive features you need to keep in mind. First of all, we typically don't know what the users want to do with the data in the end. I mean, we have some understanding, but the idea is really that all these applied researchers, they have their complex models, different analyses that they want to fit, and we don't know in advance what these goals will be. Then data are often collected using complex sampling designs. And what I mean by that is we typically don't collect data. It's not a simple random sample from the population, but there are different ways to sample your units that you want to interview to try to make your estimates more efficient, or there could be cost reasons why you use designs like stratified sampling that we already had in one of the talks, or cluster sampling. So this is important to consider. And then what's also special to official statistics, I think, is that people often think in the design-based world. And design-based is design-based inference is very specific, I think, to official statistics. So the idea here is you don't think about the data coming from a model. So it's not model-based. You don't think about a data generating process, but you only think about the uncertainty in your estimates coming from the fact that you only have a sample and not the population. So the randomness really comes from sampling, not from any underlying process with a random error. It's really the uncertainty comes from sampling. Okay. And so this is really a different way of thinking about all this. And what's also maybe a little bit unique to official statistics is that a lot of interest goes into estimating totals and means, which sounds relatively simple. In practice, due to these complex sampling designs, it's not always that simple. But a lot of people, in terms of, you can think of estimating the unemployment rate, things like that. These are important political figures, but basically they are just means, right? And then another aspect to keep in mind is that the users of the data are not necessarily well-trained statisticians or computer scientists or whatever. So they don't really know how to apply complex adjustment methods, for example, if you want to correct any biases or anything you have in your estimates. And so what I think the consequences of this are in terms of a useful implementation of differential privacy is, first of all, a classical query response system, in my view, is extremely difficult in the sense that since we don't know what the users want to do with the data, it's very hard to define an appropriate privacy budget and decide how to distribute that among the users, because it's very hard to imagine that you would say, you know, we had that survey, it was very expensive, and yeah, we know the taxpayers basically paid for that, but you know, the privacy budget is used up. Nobody can have access to the data anymore. So in that sense, I think in this dynamic setting that we have here, it's very hard to implement that. The next thing, as I said, it's important to understand the properties of the estimates that we finally get from our noisy data. And we need to account for these complex sampling designs as well. So we want to account for two sources of uncertainty now. We have the sampling uncertainty, and we have the uncertainty from noise infusion. And we want to take both of them into account. And then finally, we still want to try to keep it simple for the users, because as I said, they have a hard time, you know, if you need to use complicated, say, MCMC methods or anything to get the correct answers from the data, this probably won't work in practice because users would not actually apply these complicated methods. So what does that mean in terms of trying to get valid inferences from a differential private data set? So my assumptions here are that the goal is really to generate differential private synthetic data so that users, you know, can do whatever they want with the data afterwards. And to keep it simple, I'm only considering the geometric mechanism here. Okay, I know the geometric mechanism has this disadvantage that, you know, you have a lot of noise in the aggregates, and the Census Bureau now has more clever ways of dealing with that problem, but I just want to keep it simple here to illustrate the main ideas. Okay. So the geometric mechanism, so we would turn all variables, treat them as categorical, do a full cross classification of all the variables, and then add this random noise from the two-sided geometric distribution. And then finally turn that noisy table back into microdata. Of course, that last step from a conceptual perspective is not really necessary. I mean, there's no difference whether you have the noisy table or that noisy microdata. But there are situations users are used to having this microdata. So I think, and as John mentioned yesterday, for example, in the system of the Census Bureau, their table builders actually expect that the input is microdata, right? So they wouldn't even accept the noisy table. So we have to turn them back into microdata as a situation. Okay. So if we use the geometric, I like the geometric mechanism just because it's very simple and appealing in various ways. First of all, just because we have that integer random noise, of course, which ensures the integrality of our final noisy tables. And then also because it's very easy to look at the expected value and the variance of that. Noise distribution is very simple, which makes it also very easy to incorporate this extra uncertainty, the noise uncertainty, into the final inferences. Okay. So coming back to the means and totals that I mentioned previously are very important in official statistics. What would that mean if I now analyze my noisy data set and want to account for that extra uncertainty? The first thing, of course, is the means and the totals are still unbiased, which is nice because we don't need to use any bias adjustments. Right? We can analyze the data directly. And then if we're interested in the uncertainty that we have now in our estimates, so assume we're interested in estimating the uncertainty in a total that we want to compute. It's very straightforward because I simply need to look at the number of cells in my noisy table that I need to aggregate over to get the total I'm interested in. And since I'm adding noise independently to each of those cells, I can simply say the variance of my total now is the variance of my noise distribution times the number of cells over which I aggregated. So that's very simple and very easy to compute. Okay. And if I'm interested in the mean, it's a little more involved just because the mean now is a ratio of two random variables, so it's not that straightforward to derive the variance for that. But I can use simple Taylor series expansion, which is what survey statisticians basically do all the time when they try to estimate the variance for the means. And if you do that, you basically get to this. So again, say if I'm interested in the unemployment rate, so I need to compute the number of people that are unemployed, divided by my sample size. So I have this ratio of two random variables. But I can compute the variance very easily because I still have only these variances of the totals, which I know they are very easy to compute. I need my totals. And I know they are unbiased, so I can simply plug in those estimates from my noisy table. And then I have, again, the variance here of my random noise. Okay? So still estimating the uncertainty in the means is relatively straightforward. Okay? And just to show a little example how that will work in practice, I use some data from my institute. So I'm working at the Institute for Employment Research in Germany, and we have a very large administrative data set. I'm like, whoa. I hope this is still working. Yeah. Okay, good. Which comes from our Federal Employment Agency, so where we have information on employment of everybody living in Germany, on their history in terms of receiving unemployment benefits, participation in labor market programs, etc. So it's a very rich and very popular data set at my institute. So a lot of people like to use that. And recently, very detailed geographical information was added to the data set. So we have geocodes now on the square meter grid level for each individual, which of course makes the data set very easily identifiable. I mean, you can identify basically almost everyone in the data set very easily just based on that information. And so the question was, how can we deal with that problem? And so one way of thinking about dealing with the problem was in terms of, could we maybe turn that into a differentially private data set? Okay. And for this illustration here, I keep it very simple. So assume we would only release 4 variables. So we have sex, foreign status, employment status, and the zip code. Okay. And now my user of the data is the mayor of the city of Fürth, which happens to be my hometown. And he's interested in just computing 4 quantities: the total number of unemployed, the total number of unemployed foreigners, the unemployment rate, and the unemployment rate among foreigners. And the question is then, will he still get valid results on that protected data set? And I'm using a simple repeated simulation design where I generate 5,000 differentially private data sets using the geometric mechanism, and I'm setting epsilon to 1 here. Okay? And this will be the results. So these are the true estimates for my 4 different quantities of interest. So I have the first row, these are the true values, and these are the average estimated values across my 5,000 replications. And not surprisingly, they are unbiased, which is, of course, an important useful property. But then here I compute the variance ratio. The variance ratio is just, I computed my estimated variances in each of these 5,000 runs based on the variances that I showed on the previous slides. And then I divide the average of these estimated variances, I divide that by the true variance of this estimate here across the 5,000 simulation runs. Right? And of course, if it's close to 1, I know I estimate my variance correctly. Okay? And so you can see in all cases, of course, it's close to 1. So we can actually estimate the uncertainty in our estimated quantities of interest validly. And then I have the confidence interval coverage. So we typically compute these 95% confidence interval coverages, the 95% confidence intervals to get an estimate or to express the uncertainty in our estimates, right? And the idea, of course, of this 95% confidence interval would be if I generate 5,000 samples and always compute that confidence interval, my true value will be within that confidence interval 95% of the times. That's the definition of the confidence interval. And so I basically looked at that matrix. So I checked across these 5,000 simulation runs, how often is the true value included in that 95% confidence interval? And of course, it should be included 95% of the times, and this is also what I get. So in that sense, from a statistical perspective, that's great. I know I have unbiased estimates, and I know how to quantify the uncertainty. Okay? And the final thing here is just the average length of the confidence interval, which is basically telling me something about the uncertainty that I have in my estimates. And of course, since I'm only looking at 4 variables here, there's not too much noise introduced here, so there's not too much uncertainty from the noise infusion at that point. So I get pretty good estimates of the true value anyway.
Is the IEB a population register?
It is. That's right. Yeah. But now, in most cases, we don't have the full population, right? I mean, apart from the census that John is dealing with, in most cases, statistical agencies will collect their data based on surveys, right? And as I said before, it's hardly ever the case that simple random sampling is used here. So we have all these different complex sampling designs, and there's a long literature on how to account for these designs in terms of variance estimation and in terms of getting the right point estimates also from my sample data. But the important aspect, as I mentioned before, is now I have to consider 2 sources of uncertainty. I have the sampling uncertainty, and I have the uncertainty that comes from noise infusion. So I need to consider how to deal with that. And the good thing for us is that the noise is really only infused to the sampled cases, right? Not to the population. So we first have our original data, which is the survey now, and then we add noise to that, which makes it pretty simple to also account for that in the analysis, because we can basically think of that as a 2-stage process, right? We first draw the sample, collect the data, then we add noise to that. But that's conditional on the sample. So if I look at my expectation, I don't want to go through all these details, but the important thing is, so my theta hat here is my estimate of interest. So again, some mean or some total, potentially for some subsets of my data set, right? And I can still say this expectation of that estimate that I get from my noisy data is still the true value. So I'm still getting unbiased results based on my survey data. Of course, still assuming that we are using the geometric mechanism here. Okay? And the good thing regarding the variance is, given that I have this 2-stage process, I can use a very simple, I can simply use variance decomposition to say that the final variance is just the sum of these 2 variances, which again makes it relatively simple.
Are you going to show us your DP estimator?
The DP, I'll come to that. Yeah. So now I just have the variance from noise, and I have the variance from sampling. Okay. And of course, I don't know the true variance from sampling, but I can simply use the estimate for that variance from my noisy sample. And at least for the geometric mechanism, again, it can show that this will be an unbiased estimate, at least for certain sampling designs for the true variance. Okay? So let's look at an example. Stratified simple random sample, which, as I said, is pretty common with statistical agencies to improve the efficiency, because you can show that your variance from sampling will decrease if you use stratified sampling, and also to ensure that you have sufficient sample sizes in certain subdomains you're specifically interested in, because you can ensure that you sample enough records for that subdomain. Okay? So it's very simple. You simply divide your population into H mutually exclusive and exhaustive strata, and then you take simple random samples without replacement within each of those strata. Okay? And if I define pH, pi-h, to be the sampling rate within my stratum H, I get the following final estimates. So, yeah.
Just for clarification, this stratification of the population, is it based on attributes that could be potentially sensitive?
That's a good question. If they are, things get more complicated. So in my situation, I assume they are not. So for example, in the example that I show later, I would use the zip code for stratification. And I mean, it's hard to, consider that to be, that information is public. I don't know how you would argue that this is sensitive information.
The zip code is not public. Little n over big N in the zip code is not public.
It is not. And maybe we should discuss that right now, because I expected that question. But I think, and that is something we can argue and discuss, but my argument would be that the sampling rate itself is, at least it's a little tricky to think about it in a differential private concept, because the sampling rate is fixed before anybody will be sampled, right? So in that sense, thinking about, how would that pi change if someone joins or leaves the database, does not make much sense, because it wouldn't change. Yeah. I'm only talking about the sampling rate, not about the, if you account for non-response, that's something different. But the initial sampling rate, that doesn't change. So this is a fixed number. So in that sense, you don't need to think about, how much would that change if somebody leaves or not. But I agree in some sense that you could argue, I might be learning the original sample size, maybe.
I think your design is simple enough, so the exogenous sampling assumption is probably justifiable. You had those weights available to you. You could have processed them through their own estimation system with DP to get the weights, and then this works by composition.
Right, so
most of the time, you do all sorts of post adjustments to those weights that are based on the characteristics you actually measure.
Right. I have a comment on that at the end of my talk, which I agree, that makes everything way more complicated, and I don't want to go there right now. Right. Yeah. Sure.
Sampling variables are exogenous, or you said you used a technical term like sampling weights are exogenous or something. What does that mean?
I only heard the last word.
What was the question?
What exogenous means when you said the sampling weights are exogenous.
It means that those pi's in his formula came from public information.
Okay.
And are
don't
not influenced by the values you observed in the sample.
right.
And that is not are you saying that's not realistic, or is
The final weights.
It's not zero probability thing, but it's very unusual not to adjust them, typically for non-response, and that's usually done stratifying on the basis of characteristics you observed in the sample.
Yeah. So I'm really only talking about the design weights here. So this is what the technical term is, design weights. These are the ones that only depend on the sampling rate and not on any adjustments that will be done later on. And I'll come back to that. Okay? But anyway, my estimates, as I said, are still pretty simple because this is the standard estimate for a total if you have stratified sampling, so you don't need to adjust anything. You just treat your noisy data as if it would be the original data, and you can get an unbiased estimate of the total still. And for the variance estimate, as I said, we now have these two components. So this is the variance that I get from my sampling, and this is the variance part that I get from my noise infusion. But I still can compute that very easily. Okay. So that's the good thing. So again,
Another question.
Sure.
Did you adjust epsilon to reflect the sampling?
I could. I don't do that in this simulation study that I'm showing, but you know, I wanted to say exactly that. So now I take a 10% sample, so I'm still using an epsilon of 1, but you know, you could argue that this is comparable to an epsilon of roughly 0.1 now, because I have a 10% sample and I have that secrecy from sample. Yeah. But I mean, it's only a simulation study anyway, so it's not like I'm saying this will be the epsilon that I recommend to use or anything. It's just illustration. Right? So we use the same 5 variables, but now we use the city of Munich just because it's bigger than my hometown and I need to take these samples. So I'm using the city of Munich. And I stratify my data by the zip code and then take a 10% sample within each of the zip codes. Okay, so this is my stratified sampling design. So this is the way the original data would be collected. Okay, and then everything else stays the same. So I use the geometric mechanism to do the noise infusion. And then we basically still have exactly the same results. My estimates are unbiased. My variance estimate still works. My coverage rate is okay. And the nice thing here, I think, is that the user could actually learn what's the relative increase in variance due to the noise infusion. Because the good thing is the user can actually compute both quantities, right, based on that formula. So this is the variance from sampling. This is the variance from noise infusion. So he would already know what's the price he pays in terms of the privacy of the data, right? And so in this case, we have an relative increase in variance due to noise infusion of about roughly 10%. Yeah.
On the variance, so for the uncertainty coming from sampling, it's kind of a setting where central limit theorem should apply. But that's not the case for the noise coming from privacy, because it's not like a sum of independent indicator random variables. Does that affect how you think about like is capturing the uncertainty by the variance and how you translated that into a confidence interval? Is that something you worry about, lumping them together that way? Are you using a normal approximation when you do your confidence interval?
Right. Yeah, good point. Yeah, I'm using the normal approximation exactly, and you can argue that it's questionable, especially I think it will become. I mean, at least in all my experiments that I did so far, I never run into any problems. No, it worked, but it might be a problem if we look at very small subdomains. Because I mean, otherwise I'm adding up all this noise, right, to get to the totals. And so the sum of all these noises, I mean, there you get that normal approximation again. But otherwise, if you would look at specific cells in that noisy table, I agree, you would have to.
No, you don't.
Why not?
Because the number of entities that you add to the numerator and the denominator doesn't go to a constant unless you control it. So somebody had my picture up yesterday of using unit by unit, in your case cell by cell differential privacy, on the block, tract, county, and state level estimates, or I think they might be national. And they never improved, even though you were doing exactly the aggregation that you just described. And it's because the differential privacy noise doesn't cancel out the way.
Yeah, it's not. The idea was not. The question was not about whether it cancels out. It was only about whether the normal approximation is justified. And
That's the point.
I'm not sure. I'm not sure, but we. What?
You don't need it to calculate the variance.
Yeah, that's right. But the question is for the confidence interval we need it. And the question is whether that is justified. And I would argue that as long as you don't look at too detailed cells in your final table, it should be. We can discuss that later if you want. I think I'm running a bit out of time. Yeah, that's okay. Because one thing I still want to talk about is this problem in terms of negative cell counts in the noisy table. Because obviously in practice we don't only have these 5 variables typically, and so my fully cross-classified table will be sparse. And so I have all these issues with these negative cell counts that you all know about. And of course, this is especially problematic if I want to turn my data back into microdata, because I just don't know how to generate -2 for an unemployed people in my data set, right? And so there are a couple of ideas in the literature. The simplest one is to simply set the negative cell counts to 0, which of course is not a very great idea because you introduce bias, because you're drawing from a truncated distribution now. There have been other ideas using the Fourier transformation. I must admit, I've never tried to apply that, so I don't know how well that will work in practice. But I think what's also been done what's currently done at the census is to use linear programming, right? To find a solution that's still as close as possible to the noisy table, but you have these non-negativity constraints here, okay? Which makes sense, but the problems that I see with these approaches, with any of the approaches, is you lose that guarantee of unbiasedness. So your estimates will no longer be unbiased because of these adjustments. And it's also very difficult to think about, what would you do now about your variance estimates? It's, at least for me, I cannot figure that out. So I thought of a different solution, and that's based on calibration. So that's something we do all the time to adjust for non-response, or if we have undercoverage, so if certain people don't even show up in the sampling frame that we use to draw our sample. And the idea here with this calibration is to generate weights which ensure that the estimated totals from the database match some known totals I have from the population. Typically, census data is used for that. Okay? And our problem, of course, is we cannot use any information from the original data without spending some privacy budget. You could do that, but I want to do something else, because I can still use the unbiased counts from my noisy table. Okay? And I use them for calibration, because for them I know they are unbiased. So my solution would be, we generate our DP table first, we add noise to that, then set those negative cell counts to 0 to be able to turn it into microdata. I'm turning it into microdata, which I know will be biased, but then I generate these calibration weights to adjust my estimates back to the totals I have in the noisy table. Yeah?
How different is generating microdata and then calibration weights from directly adjusting the probabilities in the table? You don't have a notation for the.
The problem is, I think I know what you mean, but the idea would still be, I want to release this microdata in the end, where I have individual records instead of the table, and there I cannot use these probabilities.
Let's say instead adjusting the probabilities in the table and then sampling from those. I'm just trying to understand how different it is to add weights to the sample, to the microdata sample, from simply like you could take those weights and multiply them through the probabilities that you were using to generate things and generate. For example, imagine you've got a sample with weight 2. You could, mathematically, it's equivalent, I think, to just duplicating that sample, to having 2 copies of that one thing. And so I'm just trying to understand how different this is.
I mean, I think it's relatively similar, but what you would do is then you would have, I think, because you cannot, I mean, you could sample with these probabilities, but then you would have another round of expectations required that only over this sampling design, again, you need to take additional expectations. I think it would increase the variance.
Okay.
I would have to think about that. Good. But anyway, so this is this calibration approach that I'm suggesting. What are the advantages? I know that my estimates now will again be unbiased based on my microdata. And since I'm calibrating to all the cells in my noisy table, I don't even need to adjust my variance estimates. So I can still use those variance estimates that I used before. Of course, the disadvantage is if I had negative values in my noisy table, I will still get these negative estimates then based on my microdata. So some users might not be too happy about that, right? But at least I know how to get unbiased estimates and I know how to do the variance. If I want to avoid these negative estimates based on my noisy microdata, I could only calibrate to certain aggregates in my noisy table. But then the price that I pay for that is that this unbiasedness property will only hold at that level of aggregation for which I use the calibration. Okay, so anything below that, I cannot make this unbiasedness guarantee anymore. Just an illustration very quickly. So I use a few more variables now from that same integrated employment biographies. Use the same simulation design. I don't have any sampling anymore. I don't use the exact geocodes, but I aggregate them to build clusters of size 50, which of course is still pretty detailed on a geographical level. So now I have a sparse table because my original data only contains about 40,000 records, but my noisy table consists of more than 160,000 cells. So I'll get a lot of negative estimates in my table. And I'm comparing the naive approach where I'm simply setting all negative values to 0 to the calibration approach. And with the naive approach, as expected, of course, I'll introduce bias. I have totally biased results, so that wouldn't work. But with the calibration approach, I'm back again. So unbiasedness, my coverage is OK, my variance estimates are OK. So in that sense, I think that could be a useful approach, maybe. OK? The conclusions very quickly. I think I can go over that very fast. The only thing that I wanted to mention in addition is, given that everything is so simple, I think this could be something that could even be integrated. Say, if the Census Bureau would provide these tables, they could provide measures of uncertainty with these tables already, even for the census, so that people know, we have these noisy estimates, but we know what's the uncertainty that we have in these estimates, okay? Which might be a nice feature. But of course, there are a lot of open questions. I think that's one of the key themes of that whole workshop here, that there are still a lot of open questions. So, of course, the things that happen at the census are more complex. We have these hierarchical levels where all sorts of adjustments happen. And so it's much more complicated to think about how would you incorporate that. Would you still get unbiased results? How do you get the correct variance estimates here? So that's something to think about. And then if we have different sampling designs, and as John already mentioned, if we try to account for non-response and calibration, things get much more complicated because we now use information from the data, so we would need to make that differentially private. So things get much more complicated once we get to that stage. And of course, I only talked about totals and means. So what about all other types of analysis, right? Regressions, whatever. And then, of course, in the end, will the final loss in accuracy, even if it's unbiased, but if we have a lot of variance, would that still be acceptable in practice? OK. Thank you.
We have a couple of minutes for questions.
Can you say a little bit more about when you do this calibration?
Yeah.
What is released to the what's published? So that
yeah.
Before you were saying you wanted to publish microdata.
Yeah.
So now is it?
It's still the micro.
160,000 each with a weight, or
no? It's the not the 160,000, because that would be the table, right? No, it's the microdata generated, so the differentially private microdata, which would be about 40,000 records, maybe because the original sample was 42,000, right? And each record would have a weight attached to it. And the user would use that weight to get unbiased estimates. So this is something, as I said, which is common in the survey sampling literature. So assume you want to estimate a total. Instead of simply summing all the axes in your data, you sum the axes multiplied by their weight.
So where do the negative counts appear in that? They appear as negative weights?
Yeah, exactly.
So it will actually be more than 40,000 things, just the sum of the weights will be 40,000? Because,
yeah, right. The sum of the weights would be equal to the, no, the sum of the weights would be equal to the population size and the original population size.
But that is not uncommon. I mean, negative weights,
yeah.
we know how that works, right?
Oh, no, I don't know what that is.
Yeah.
So that's okay.
No, I mean,
All right.
but people wouldn't be surprised by that, you know.
You could do the calibration using an exponential function, you know, and avoid negative weights. There are ways to avoid negative weights.
Yeah, but you cannot avoid the negative weights here because we are calibrating to negative table counts. So you have to have negative weights here.
Oh, I see.
In that sense, you cannot avoid that.
Very quick
Just a clarification, how do you get a negative weight? Because if you get a negative count, then you round up to 0, so you would never sample a record matching that characteristic.
That's a good point. I didn't include that in the slides because of time. What I would do is I would check my noisy table, and then if I have that situation where I don't, I mean, I basically, if I have a 0 count, of course, in my adjusted table, I would never have any record that has these properties of that specific cell. So I'm simply generating some. Because, I mean, again, it's post-processing, no problem with that. I just generate just one record, and this will get the negative weight attached so that it matches the negative cell count.
So you get one for every single...
For every negative cell count in my noise.
So, unfortunately, I suggest we take further discussion during the coffee break because we are already behind schedule and there are people watching live stream. So let's